let's start. Welcome to this final session on the hands-on session for this summer school. Let me share my screen. Nothing here. Which will be dedicated to the simulation of high cycle fatigue processes. Yesterday, we dedicated some time, 1 hour and a half, to start introducing the modeling of another nonlinearity, the damage, okay, and how to model that on Kratos. And the idea for today's session, let me just okay. This is not necessary. The idea of today's presentation is to continue with that topic, but now extending it to the simulation of fatigue, high cycle fatigue in particular. So we will continue with this. The first thing, this is the QR to download today's presentation as well as yesterday's presentation, as well as the models that I shared with you yesterday. So the IGS file for the quarter of the sample, the tensile sample that we studied. There is a new geometry for today's sample, which corresponds to a standard high cycle fatigue sample. I'm also sharing with you a CSV file. A CSV file? No, not a CSV file. I'm sharing with you an Excel file with a tool to calibrate, to do the calibration of the high cycle fatigue model. Okay, these 4 to 6 parameters. Let me just show to you what's in there. So basically what you will be downloading for today's session are these 4 files here. You have one GID case corresponding to one element case that you can use to just do some trials with the high cycle fatigue model. In here, you will have everything, the geometry, but also the input files for Kratos. So you can check in here, for example, for the structural material JSON, which is the structure of this high cycle fatigue to build the high cycle fatigue case with the corresponding new variable defining the properties for the fatigue response of the material, as well as all the variables that we introduced yesterday to calibrate the damage response of the material. Okay. Apart from this, you have the presentation for today's session, this geometry corresponding to the second example that we will be seeing today. And finally, we have this Excel file here, which is this Excel that I prepared containing experimental information. This here is experimental data coming from SN standard tests, as well as this here, which is the model in a synthetic way, the formulation of the mathematical description of the Buller surface that we are using for our model, so that by changing the values in yellow, this chart here will update. And the idea, well, we will do that later, okay? But the idea is that you can play a little bit with these calibration parameters to see if you are able to capture the points coming from the experimental tests. So for example, this here is the fatigue limit. And if I switch it to 150, well, it seems that nothing has changed, but it has changed. Okay, if you can see, curves are changing. Okay, so the model is prepared just to take into account the information in the yellow boxes. This is the data to be calibrated. But let's move back to the presentation. And let's talk a little bit about, let's remind you the main concepts or the main features of the fatigue model, and then we will proceed with the examples. Okay. So this is the structure for today's class. We will this one is 2 hours instead of 1 hour and a half, so we will have some time to discuss in case that you have questions. So this is the structure for today's class. We will start by introducing the high cycle fatigue model in the context of, in the framework of Kratos. So let's see how the input files need to be modified to account for the fatigue response or the fatigue behavior in a material. And then we will discuss a little bit about how to take the how to.
So sorry. Could you please share the screen?
I'm not sharing the screen.
Okay, thanks.
No. Okay, sorry about that. Okay, now you should be able to see the screen. Okay. Do you see it? Yes. Yeah.
Yes.
Thank you. And then we will continue with some examples. Okay. So let's talk about this. Let's review the concepts of the high cycle fatigue model. So basically, as Lucia introduced you yesterday, and as we have been mentioned during other sessions, the high cycle fatigue model is indeed an extension. The way in which we are formulating it in Kratos is basically an extension of this isotropic damage model, okay, the one that we used yesterday to perform the simulations. And on top of this isotropic damage model, we are defining this new function here. This is a function that reduces the properties of the material that we are studying as the cycles are being applied on the material, on the model that we are studying, okay? And on top of this base model, in order to make it functional from a general perspective, because high cycle fatigue involves a lot of time to develop, we are introducing this advanced in time strategy. Okay, this advanced in time strategy is the one allowing you to skip this initial part of the simulation in which everything looks like if it's elastic, and going then directly to the inelastic part in which both the fatigue evolves as well as the damage. Okay, this is the idea. So let's see what we have in here. Regarding the isotropic damage model, nothing new. Okay, this is the structure that you have in Kratos to introduce or to define a material which behaves according to an isotropic damage model. So you have some elastic properties. This is a plane stress case. You have some elastic properties as well as the thickness. And then we are defining some variables to describe the nonlinear behavior in our material, basically the yield, the fracture energy, and depending on the softening type, this is exponential softening. But if this is 3 and so we have also hardening, we need to add some other variables, okay? But that's it. This is something that I explained already yesterday. So nothing new indeed here. Then, this data here, as we've seen yesterday, is these are data to be calibrated according to tensile test or according to the monotonic response of our material. Okay, and then we move to the calibration of the fatigue response of our material. How do we calibrate, and how this then reflects on Kratos? Basically, on top of these basic variables corresponding to the behavior, to the damage behavior of our material, we are adding this new variable here, high cycle fatigue coefficient. This goes on the structural material JSON file. Okay, so we are adding a new variable there, and this contains the various parameters that we were mentioning while we were presenting the model. And I'm giving you some key words about or some hint about the meaning of these parameters here. Lucia focused basically on this alpha term, which is basically related with the SE, which is the fatigue limit in our material. This is the minimum stress that you need to apply into the material to develop fatigue degradation. Okay, so below this stress limit, there is no fatigue degradation developing in your material. But we are adding this information by means of alpha, which indeed is SE over SU, the fatigue limit over the ultimate strength of the material. This is for the experimental guys, this is the UTS, the ultimate tensile strength of the material. Okay, then we have some data here. Let me focus first on alpha F and beta F, which are parameters to calibrate the most important region of our Buller surface, which corresponds to the R-1 stress ratio. This is R equal to -1. The stress ratio is equal to the minimum stress of your cycle over the maximum stress of your cycle. So the -1 case corresponds to a cyclic load in which the minimum and the maximum are equal, opposite sign. Okay, so you go the same, you are applying the same stress under tension and under compression in your material. Okay, so fully reverse cyclic load. And this is the most restrictive kind of load that you can apply on your material. So for this most restrictive case, we have two parameters that needs to be calibrated, alpha F and beta F. And they basically change the behavior of this curve here, of this line, not the surface, just the line. Okay, of course, the surface is kind of conditioned by these two values, but these two values are the only ones affecting this line here. The other parameters do not affect this line here. Of course, SE, yes, but not the other four parameters. Okay. Then, apart of these two alpha F and beta F parameters, we have these STH parameters and auxiliary parameters. The STH parameters, let me focus for the 1 values, okay? The aux are 1 and the STH are 1. This STH R1 parameter is the one responsible to fit this region of the curve. Okay, if you have a look on our formulation, what Lucia introduced yesterday, we were defining a function which is STHR. This is a function that depends on the stress ratio, and basically this is the value of the Buller surface, which is written as a function of the number of cycles and the stress ratio, when the amount of cycles is or tends to infinite. Limit when the number of cycles tend to infinite. This is equal to STHR. Okay, so basically it's this function here, and this function depends on this term here, on this parameter STHR1. Okay, the STHR2 is a parameter that also is needed to calibrate this function, but outside this regime. This regime here that goes from R-1 to R1 is what it's called the tensile dominant type of cycle. Okay, the cyclic loads that result in this or that are accounted in this regime here are those in which the tensile stresses are more significant than the compressive stresses, which are the type of loads that are considered to drive the fatigue kind of degradation. Okay, so this is the region that we will be indeed calibrating. So for the other terms, you will be setting a dummy value. You can leave it as it is, as I'm you can leave it as a dummy value using the value that I'm providing to you. Okay, and then the auxiliary R1 value, this one here, is a parameter controlling the curvature of this part of the surface. Okay, by calibrating these four parameters, STHR1, alpha F, beta F, and auxiliary R1, you will be able to calibrate this surface. Okay, how do we calibrate this? Well, according to experimental information. In top of this surface, we have these blue points corresponding to experimental data that has been obtained on the laboratory for normalized samples. Okay, so then we will take this information and we will be fitting our surface on top of this. Okay, and by doing that, we will be calibrating our fatigue model. This is the idea. So let's change now to the next slide. And this is This is the resulting vector that we will be introducing in the material JSON, the structural material JSON. This term here, this is alpha. This term. This term here, this is STH-R1. This here is alpha F. This is beta F. This is, sorry, this is not alpha F and beta F. This is the dummy value that I was mentioning, the STH-R2. This now is alpha F. This is beta F. And these two here are the auxiliary R1 and auxiliary R2 parameters. Okay, so you will be introducing this vector, and this is the information that the Kratos will need in order to perform the simulation. If you remember, Lucia yesterday also talked about a C parameter. That was the one that allowed you to change the evolution of the F red on this initial region of the curve. This is your F red function, okay, on top of this Buller surface, if you remember. So this is the F red corresponding to this specific stress ratio and for this specific maximum stress, okay? Or for here, for this one, your F red corresponding to this value here would look something like this, okay? This is the F red, the fatigue reduction function that is the one that will tell the model how the material properties evolve while you're applying the cyclic load. This here is the definition, or let's say the shape of this F red function is not unique. It depends on the C value. By default, this is 1, okay? But if you change this value, you can end up having F red surface, F red functions that also meet the same conditions that the original F red for value 1, but with different shape, with different slopes, like this one or maybe this one here. And all of this is being defined by the value of the C. But in here, we are not specifying C, okay? There is a way to specify a value for C, which is adding more terms here after this, but we will not use this onto this session, okay? If you are interested, we can discuss this, how to introduce the C, how to characterize C, but we will not be using this for today's session. So this is the description of the structural material JSON. Now, focusing on the final part, which is basically the advancing time strategy, what we will be doing is going now to the project parameter document. So instead of in the structural material, we go to the project parameter, the other input file in Kratos, and we will be introducing this block. Okay, this block is the one telling to Kratos that you want to use the advancing time strategy. You have it here. Advancing time strategy, true. If you set this to false, then you will have no advancing time strategy. Okay, so this must be set to true. And then in here, you have some other parameters. Let's start with, I think that Lucio did not go into that detail yesterday. But anyway, the advancing time strategy basically allows you to skip certain amount of cycles of your simulation, okay? The criteria that it's being used to define the amount of cycles that are skipped during a simulation can be adapted or can be defined or specified for each simulation, okay? There are 3 ways to characterize this cycle jump, okay? The first one is to make it in an automatic manner. This is, you will start the simulation, you will see that you will be doing a couple of cycles, and after these couple of cycles, you will be jumping, okay? And you will be jumping up to an amount of cycles that results on the initiation of non-linearities based on damage variable, okay? So, and this is automatically controlled by the model itself. But the user can define these other two parameters. So for the first option, you do not need to define anything. And then you have two other options. This one here, which says advancing strategy in cycles. So you tell to the model, okay, I'm only allowing you to do jumps, of 100 cycles. So every time that the stability conditions that allow to trigger the advancing time strategy are met, then this here will be done. Okay, so this is an integer. This is an integer ranging from 1 to infinite that will tell to the model the amount of cycles that you, or the criteria to define a certain maximum amount of cycles that can be jumped during the advancing time strategy. If instead of cycles you want to define a time criteria to perform the jump, you can do it here. Okay, and then the advancing time strategy will look at the three criteria, so the automatic option based on initiation of damage, the maximum amount of cycles, and the maximum amount of time that is allowed to jump. And depending on the minimum value, the advancing time strategy will perform that jump. Okay, so that's why in here I'm setting dummy values, really big values, because I don't want to go with this criteria, and I just want to have this automatic jump of the model. Okay, so basically you will be comparing 1 to the power of 12 cycles against 10,000, and the criteria will be 10,000, which is the automatic jump. Okay, nothing else indeed. Well, yes, there is an extra parameter that needs to be included. I'm not sure if it's in here. No, but there is an extra parameter or an extra sentence that needs to be input in the input files in order to be able to use the advancing time strategy. But I will comment that later, because it's just a line, and indeed you do not need to define anything for that. So these are the inputs, okay? So indeed, you will be using the same input files that you were using for damage, only in 3D. This here, the high cycle fatigue model, is only available for 3D cases, so you cannot use that for plane stress or plane strain analysis at this moment. Well, I'm working on that, but at this moment, this is only available in the problem type for 3D elements, okay? So you must create a 3D geometry. So it's just taking the input files that you've created for your damage simulation and include one extra variable for the structural material JSON and this fatigue block for the project parameter JSON. And that's it. And you can run the simulation, the high cycle fatigue simulation, with no problem. Okay. Then what's in here? This is the correlation between the FRED function, which is the function that it's controlling the evolution of the properties of the cyclic properties of our material, with the Buller function that we've created to capture the experimental results for SN data. Okay, so this function here, this is a mathematical expression. This here is a mathematical expression corresponding to a surface. This here is, let me just, well, it is indeed this here. This W function is the one representing this surface in here, okay? So the good the good thing is that this Euler surface, this function for this mathematical representation of the Euler surface, is described using exactly the same parameters that we've used to propose this function here, which is the FRED function. Okay, so by calibrating the parameters in this function here, these are the parameters to be calibrated. This here depends on alpha f as well as on auxiliary values, auxiliary Ri. This is the beta f, and this here depends on SE, the fatigue limit, as well as the STH Ri parameter. Okay. So by calibrating these parameters here for the Euler surface, you will be at the same time calibrating this function here. Of course, you will be missing the calibration of C, because in order to being able to calibrate C, you will need some extra data, but we will not be calibrating C for today's session. Okay, and this is the well, this is something that I've already commented. Okay, so the point here is that alpha, this relation between SE and the ultimate strength of the material, is the only parameter that has some physical meaning. Okay, basically then these 4 parameters here are parameters to be calibrated based on experimental data, but they do not have a physical meaning. So you cannot go parameter by parameter and find a number that can be correlated with something observable, okay, on the measures. All the parameters need to be calibrated simultaneously. And then is where we will be moving to the Excel file, and I will give you some minutes to try to see if you are able to calibrate values for these parameters here. Okay, so you can give a try and try some values for these alphas and see if you are able to capture these behaviors here. You are calibrating a surface. Okay, so you can do it. You have the file and you can play with the numbers here. I'll give you 5 minutes. Here you can see the QR. Okay, for those that missed the QR, here you have it. So you can download today's presentation and yesterday's presentation, as well as the files needed for these sessions. The experimental data that we are using are the ones corresponding to the stainless steel that we were studying yesterday. Okay, so yesterday we start studying the monotonic behavior, the tensile response of a stainless steel, and this is the results that are obtained experimentally for Essen tests. Okay. How is it going?
I just try to like, you should just play with this already.
As well as the SE.
It's already. And also this one.
The SE is the only one that has some physical meaning. So it's the only one that you can correlate with something which is observed with the experimental. Nothing else.
I see. What's the
Fatigue.
fatigue
The
threshold?
yes. Minimum stress to be applied on the material to the start is degradation, cyclic degradation.
Claramente una dirección surface y calibrar los puntos para que guarde con
The point is that SN has been always observed. Usually it's only represented by a line because industry is only interested on minimum amount of or maximum stress that can be introduced in the material that results in fatigue. So that they ensure that they always work below that limit. So they are only interested on the line which is the lowest one, the R minus one line. Okay? But the reality is that they cannot really ensure that the stress, the working stress will be below that limit. So you need indeed to give an answer to all the spectrum. So the let's say really it works in a continuous manner. So the Euler surface is a connection of various lines that appear depending on the type of cyclic load that you are applying. The difference between the bottom line and the upper one is the cyclic. The bottom one is R minus 1, and the upper one is R01. This is the minus 1 is same compressive, same tensile. Okay, so fully reversed. The R01 is tensile and 10% of minimum stress. Okay, so everything is under tension, but in this ratio.
What it depends on damping fatigue is you can convert any arbitrary input, let's say, and normalize it, so it's always symmetric. So the amplitude is mean is zero, the amplitude is minus one. So can you not project everything to the minus one, right?
Or what do you mean by projecting everything to the minus?
So let's say, as you said, your input is as an amplitude and an offset. Let's say. Can you not normalize the model so say the equivalent stresses that would result with amount?
But this would mean just shifting these values down.
Exactly.
But the fatigue behavior is not linear. So you cannot really do that because the surface is not a linear surface. It has some curvature. And so I would say that it's not really doable in this manner. So if have you tried to fit? Have you obtained something good? Yes? How good?
Solver.
Sorry, what?
Solver. Excel solver.
You've done it with a solver
Yes.
and obtained 4 parameters.
Yes. More or less. Yeah.
It's better than just trying random
Yeah.
numbers.
No. Pricing.
Was the first option for when I started using this sort of solution. But there are many ways to solve this. Do you know how it works, the solving in Excel?
Yeah, more or less. First, like you need to set up the objective.
Okay.
So use the functions that you have already here for drawing the curves to find the expected values of each of the actual data values. One minus the other square, so all of them together, that's a square. Use that as an objective. And then the solver, I remember I read the numerical method that it uses to, I don't know if it's
From the-
fixed point, for example.
I have
don't
never
know.
used that.
But it uses a numerical optimization method. I
Okay.
think fixed point, which is the easiest
And
one.
it solves, it obtains values for the 4 parameters simultaneously.
Yes.
Okay.
You set up all the variables that you want, and it's going to look for all the parameters simultaneously.
Okay, that's nice. I mean, and which sort of values have you obtained? Weird values, or they are look like nice values?
I don't really know necessarily. I think the C value probably sounds reasonable. 100 times less than SU. This is not very high.
So I'm not sure if this was the result or not. Let me just check that.
Which is value. Not, that's not the C value, which is probably most important.
Okay. So this was the calibration that I made. Okay. When I was doing the calibration, indeed you have the values on the material JSON, structural material JSON file that I shared with you. So if you open the one element case and you see there, which is the calibration that I was using, that was the results that I was obtaining. You know, when I started working on fatigue here at Thimne some time ago, there was no algorithm to solve this problem. Okay, and then I started working on some options to do this calibration process, and then the solution by that time was, first of all, just because we are looking for, I'm not sure if I've included this here. Yes, here it is. Just because we were doing, or we are calibrating 4 parameters, and I know that some of them are just the ones responsible for the calibration of certain values of the curve, or capturing certain values of the curve, I can do the calibration in a, let's say, more ordered manner. So not everything simultaneously, but parameter by parameter. And then you have various options. For example, in here, we have experimental data to calibrate. We can calibrate first alpha F and beta F with just this curve here. And so you can define, you have a function that is dependent on alpha F and beta F, and you can set various types of boundary conditions. So for example, you can specify that you want that curve, that line, to cross 2 points. And so by doing that, you will be obtaining values for alpha F and beta F, okay, that meet this condition. And then for the other 2 parameters, you have another set of values corresponding to R.01, and you can once more set that you want to cross these 2 points. And so you specify this, and you will be obtaining values for STHR1 and auxiliary R1. Okay, there are other options. So instead of imposing that the line will pass through a certain point, you can say that the tangent of that line at a certain point needs to have certain value. And by doing this sort of things, you will be able to calibrate also the values. And then I played also, and this is indeed the strategy that we follow now, I play a little bit with the fit function that is available in MATLAB. Okay, MATLAB has a fit function to fit parameters of a surface. So I give to MATLAB all the experimental data, or filter ones, because you have some values that correspond to run-out. So indeed, the samples in here have not failed. In this case here, these values here are not samples that have failed. So you maybe wanna discard these results here and just use the ones that correspond to failure samples. And using this experimental data and the fit function, you will end up with an automatic tool that provides you this calibration of the parameters. And this is the way that we are doing it now, using a fit function approach in MATLAB. Okay, I have not given you the routine, but you can implement it in your own if you want, or you can play with other alternatives. I mean, this is not the only option to do this calibration process, but this is working quite good. Okay, so, and this is just to show you, I was doing that. These are the results obtained with that fitting tool, just to show you that if you try to guess these values just by trial and error, of course you will never end up having this sort of values. Okay, and small changes, you've seen that everything was wrong until I input the last value. Okay, this is the result that I'm obtaining without the exact value for the last parameter. So maybe the result will be completely wrong until you input the correct numbers for every parameter. So every parameter is quite sensitive to the values that you are inputting. That's why doing this by hand, it's not really an option. Okay?
Sorry.
Yes.
Also, like some methods like this squares method, or like.
Yeah, I guess that the fit function in MATLAB is using some of these. I'm not sure what's inside, but I think that you can specify the algorithm that it's using to optimize the parameters.
And also like Newton rocks and interaction, right?
Yeah. Yeah. Okay, so this is, but in this way you have here this function is the Buller surface. Okay, so this function that is in Excel is indeed this function in here, this W. Okay, and so you can see here the values of this function, and this is basically what it's programmed inside Kratos. Instead of programming the Buller function, what we are programming is fred, but both are written based on the same parameters, so it's basically the same. Okay, now, so what we need then to being able to reach this point? The first thing that we will need is the information to characterize the monotonic response of the material. So we need at least one tensile test or tensile response as well as compressive response of the material. And once we have calibrated the monotonic response of our material, we need to calibrate the fatigue part, and so we need this sort of data. Okay, now or every time that we are initiating a research project with any company, with any industry or research center, experimental research center, we are asking for 2 sets of stress ratios. Why? Because we need to calibrate a surface, and so we need more than one stress ratio set. This, yes.
Why don't you use, for example, like Goodman law to other
because Goodman as well as Gerber is usually referred to this final part of the curve, to the infinite life. And indeed, they are kind of proposing linear conversion or so. And what we are looking for is not just the fatigue limit, but also the entire life of the material. But if I'm not wrong, Gerber at least uses proposes a function to switch from one stress ratio to another one for infinite life, but not really for intermediate points.
Maybe also for intermediate life.
Maybe with the Woolman, yes, but
maybe too simplest to
I mean, if you do not have the data, then that's perfect for sure. You need to use something. So yes. But if we can, we prefer to use the experimental data, of course. So you end having a set of experimental data as well as the ultimate strength of your material, and with this you can start with your calibration. But this is not the only thing that we need. As Lucia was mentioning yesterday, we need also to know which is the geometry of the sample that we that they use to run these experimental tests. Why? Because all this process, so let's have a look at what we have in here. This stress value, this here, is engineering stress, okay? This is that for this sample here, they are inputting a force. In the experiment, they are inputting a force. They divide this value by the initial section, and so they obtain a mean stress for the sample. And this, for the tensile test, was quite good. But this is not a tensile test. This is a fatigue test, meaning that the stress distribution on this section is not uniform. Well, not in this section. In this region here, which is the most restrictive one, this region here is not uniform. And fatigue is triggered by these points with maximum stresses. So you must take into account the difference between the mean stress and the actual maximum stress in your sample. Okay, so you need to know which is the geometry, because this difference can be quite big. This is 9.5% difference between the mean stress and the maximum stress in the sample. Okay, and 9% difference in this axis is basically going from this point to this point here. And this is 30,000 cycles more. Okay, so 10% difference plays a huge, or makes a huge difference in the results that you will be predicting. Okay, so these sort of things must be taken into account in your simulation. So then, these data that you are using for the calibration are not indeed the ones that need to be used for the calibration, because this here corresponds to engineering stress in your sample. The ones that should be used are these ones here, the shift red values. Okay, these here are amplified values taking into account this intensity factor coming from the geometry. Okay, the geometry that you will be using is this kind of geometry. This is the kind of geometry. I think this is a little bit thicker than the stainless steel case that we will be running, but the difference is about 3%. Okay, the difference between the mean stress and the maximum stress is about 3%. So this results in this change, in this shift here. Okay, so yes.
How does it work to amplify stress to have the local as a stress is a middle? What is the amplifier?
No, we are amplifying. I mean, what I'm saying here is, these are the stresses that the experimental guys are reporting as maximum stresses, leading to or driving to failure. This is a failure point. Okay, and what I'm saying is that the stress at the failure point, the point which is indeed initiating the non-linearities, is not this stress here. Is higher than this. So basically the calibration for your material, because you are not calibrating a sample, you're calibrating the material. You're calibrating the behavior of any point in this sample here. This is quarter of the sample. So basically what you need to calibrate is not the stress in here. You need to calibrate the stress at any point, at any material point in this sample here. And in particular, the ones failing are not these ones here, but these ones here with this stress. So in order to calibrate your model, you should not be using this stress, but the amplified one. How do you know the amplification? By knowing the geometry. So you take the real geometry. You just input here a little bit of displacement, and then you compare the mean stress with the maximum stress, and you compute this intensity factor.
The data of the intensity test, for example, what kind of data do you have? It's strength and
From the tensile test.
yes, you don't have the stress directly. You have the strength, the global strength of the machine.
It depends. It depends on the experimental institute, but they usually convert. So of course, what they are measuring are forces and displacements. This force here can be, or is usually, the force that is being applied by the machine. And this displacement here can be whatever. The displacement of the machine itself, the displacement recorded by a camera, or they usually also have strain gauges, and so they measure the relative displacement between the two sides of the strain gauge. Okay, so what they usually do is converting this force into engineering stresses by doing the force by the actual force, and then you need to compare this or this, whatever you want. I mean, we are obtaining both.
But the material have big stresses in the middle.
Mhm.
Your,
During the monotonic
yes,
test,
and
it's not that I mean, the difference is not that big, because in the monotonic test, the no linearities, the sample is not like this, it's more like this. This is the tensile sample. Half of the, well, 1/4 of the tensile sample. The no linearities, if you run the tensile test in your model, you will see that no linearities, even though they start here, they rapidly propagate towards the center. And the stress distribution is pretty much uniform during all the inelastic process. The problem with fatigue is that you are never entering in the inelastic process in a visible manner. You are always in the elastic regime. So the stress distribution here is not homogeneous.
but this kind of test don't work, for example, for big deformation with non-homogeneous.
Yeah, but in this case, you will stay on small strains under elastic domain. Okay, so that's why you need to do this shift. And then, so the calibration process is basically, first of all, obtaining this value for the correction factor based on the geometry. So basically converting the information that you're receiving, which is information based on a specific geometries on a specific sample, into material values to be introduced in your material. Once you've obtained this, you need to calibrate the various parameters of your high cycle fatigue model, the ones that we've been calibrating using the Excel file that I've shared with you. Once you've calibrated this, now it's just a matter of preparing the Kratos input files. So basically adding this new variable inside the structural material JSON, adding the fatigue block in the project parameters, and then the last thing that is missing is selecting the proper analysis stage. And this was the only thing that was missing. This analysis stage selection is what is being done in this statement here. If you open any of the cases that you prepared yesterday, let me just open one. So, for example, in this case here, the damage one element, the one that I shared with you, and you go to the project parameter JSON, and you go to the end, you will see here a final sentence that says, analysis stage, Kratos Multiphysics dot structural mechanics application dot structural mechanics analysis. The structural mechanical analysis is the one driving all the process. Okay, so it's telling you, it's controlling which are the steps to be followed during the simulation. Okay, so let's advance in time, let's go through the elements, let's compute stresses in all elements and at all integration points, let's try to converge the model, and so on. Okay, it's the one controlling the simulation. Just because we are, in this case, modifying this strategy by means of the advance in time strategy, we cannot use the structural mechanics analysis. Okay, we need to shift to the constitutive loss application dot high cycle fatigue analysis, which is the one that is using the structural mechanics analysis as a base reference, but it's adding the advancing time strategy. I can show you this. In Kratos, if you wanna do some developments using Kratos, and you look for the high cycle fatigue analysis, you will see that it's using the structural mechanics analysis as reference, and then on top of this, it's calling the advancing in time strategy. I'm not sure where, but it should be, this is not, in here, it should be calling the advancing time strategy. Okay, I'm not sure where is this time increment, second line. Okay, yeah, here it is. Okay, so basically it's calling the advancing time strategy, which is not done on the structural mechanics analysis. That's it. Okay, so that's why it is necessary to include this final line on your project parameter. And that's it. Then once you've done this, you are able to run any kind of high cycle fatigue simulation. So now it's time to do the examples. The first thing that I've given you is this one element case, the one that Lucia started to introduce yesterday, in which I was doing, this is something that I made for my PhD, in which I was just checking which is the features of this high cycle fatigue constitutive law. Then what I'm checking here, how does it work, advancing time strategy, how the properties of the material reduce while you are applying the cyclic load, what happens once you enter inside the nonlinear domain or regime. This is by activating the damage variable, etc., etc. Okay, so the sort of behaviors, if you run the simulation or if you open the result that I've just sent you, basically what I've done there, let's have a look at it. If you go here into the hands-on session 3 and open this one element case, and let's have a look at the structural material and the project parameter. In the structural material, what you have is basically the damage properties using the by points hardening curve, the 3 curve here, as well as the parameters corresponding to this stainless steel material that we are studying. Okay, this is in the structural material JSON. And in the project parameter, what I'm defining is a fatigue case. So basically you have here that the starting time is 0, that the end time is something sufficiently high to allow for the fatigue to propagate. We have the fatigue block here, which has the same kind of structure that I showed you. I will now comment what's the meaning of these two phrases here, these two inputs. Then I'm defining a time step using the double, because in the fatigue case, the table option is not allowed at this moment. So you must use double input, otherwise you will get an error, because the advancing time strategy will not understand what you're trying to do. Then everything else here is basically the same as for damage. And in here, you can see the types of load that I'm introducing. Loads by means of an imposed displacement. This is my imposed displacement. Basically, I'm imposing a displacement in the x direction, here, with this function, which is a sine function. Okay, and the sine function is kind of displaced. How to define this sine function? In the most general case, what you will end up having is a times sine of this pi here is to convert it properly to radians, the time over the discretization of the cycle. Okay, so basically in this case, I'm allowing to do I'm destinating 4 steps to reach the maximum and 4 steps to reach the minimum. So there are 4 steps in this process here. Okay, plus a B coefficient. This here is the one controlling the amplitude, the range of your cyclic displacement. And this here is positioning the mean value. Okay, so if this is 0, then you will be applying a fully reversed cyclic load. If this is not 0, you will be shifting the cyclic load that you're introducing in your model. Okay, you can input whatever load that you want. and it should be work well. Okay, and apart from this cyclic load, which is being applied up to a certain amount of time, and I have defined this time just to obtain a specific value in F ret, I'm applying then a monotonic increasing load. Okay, so this is a tensile load that is applied after the cyclic load and completely fails the material. So basically this starts from zero. This is zero for the first time step at which this is active, and from that, so basically what I'm doing is I'm applying this cyclic load, and after a certain amount of cycles I stop this cyclic load, and then I apply a monotonic load that results in this final failure. And the point here is that if you compare the response of this material against the virgin response of the material, so without applying the cycles, what you will be obtaining is that for virgin material, the response will be like this. So you have dissipated this amount of energy and also deteriorated the material properties in this amount of strength. You've reduced the strength of your material, and your material is now more brittle, which is basically what is observed experimentally when you do a high cycle fatigue test. Brittleness and failure below the yield limit in your material. Okay, what would happen if you do not stop applying this cyclic load? Well, what you will be observing is that at certain cycle, the non-linearities based on damage will start. How does this reflects in your simulation? Well, if you're applying this cyclic load here, imagine that this is your cyclic load, the damage variable will start evolving. This will be different from zero, and so you will be start observing a reduction in stiffness. Okay, and this is basically what you will be observing. The displacement, the imposed displacement in this case is constant, so basically you will be drawing this sort of triangle. Okay, with less stiffness as the process evolves. Okay, so this is basically what you will be able to obtain. So now, this is the first example. The purpose of this first example is for you just to play a little bit with maybe this time here. Of course, if you change the time that the cyclic load is being applied, then you need to update this parameter as well as the displacement block corresponding to the cyclic load. And this would result in more reduction of the material properties during this cyclic phase. Okay, and then you can go to GID and plot charts like this one here. This is the monotonic response that I was obtaining for this geometry, and this is the response that I obtained using basically with the calculation that I'm giving to you. Okay, if you apply more cycles, you will obtain something like this, and if you continue applying more and more cycles, you will end up failing. Okay, this is the first thing that you can do just to see how this high cycle fatigue model works. And then this is the let's say the second step, which is basically continuing with the work that we've initiated for this stainless steel material, and now calibrate the fatigue response corresponding to this material here. I'm already giving you the experimental data, the ones that the points that are in Excel file. I've already told you which is the calibration that you can use for those data, because it's the one that we're using in the one element case. But if you want to use another one, you can try to do that, and then you can try to reproduce one of these one of these experiments. Okay, and I'm not sure if I'm including the results here. Yes, you should be able to see how the damage propagates in your sample. Okay, this is the evolution of damage for a case in which I'm applying, well, for this case in here in particular. Okay, and this is the comparison against experimental results. Okay, so this is the purpose for this session, for this hands-on session. So you can start working, and I will be here to solve any question. And there are other possibilities, but we can comment them later. So you can start working. You have 1 hour. And if you have questions related to the other sessions, you can also ask me and I will be glad to answer. Have you all signed the attendee list?
No me hace sentido empezar a... O sea, para ser que sí, yo he estado trabajando en innovación, entonces la experiencia tengo.
No, evidentemente. Ya te digo yo, cuando entré a hacer la tesis, había algunas cosas que había que solventar. Una era el algoritmo de calibración. Y tampoco no es que le haya dedicado excesivo tiempo porque la herramienta me parece bastante sólida. Pero no entrar en el detalle de ver si hay cosas más complejas.
No.
Lo que sí quiero hacer es pasar de MATLAB a Python, porque MATLAB necesita una licencia, ¿sí, no?
Sí.
Yeah. Have you signed? Yes. The materialization and the project parameter.
I mean like this.
You could use the local.
Yeah, you can use Notepad or you can use Visual Studio Code or you can use Jupyter. I think it will also work there. But if you plan to keep working on this, better download Visual Studio Code. I think it's the
That
best
was
option.
yesterday.
I'm not sure. Not sure. Maybe. It's the one that I'm using. The Visual Studio Code.
Okay, good. Thank you.
Do you know Spider, no? Spider,
Spider.
no, Pasha. Nothing?
No.
Me he querido preguntarte y mostrarte las caracterizaciones del material que yo he estado trabajando en el pasado. Un pedacito de clase. En la oficina tengo una muestra de grupo para inclusión 3D. La cuestión es que claramente tiene daño, pero nosotros nos lo vamos a saltar por el momento para caracterizar el daño de su material. Entonces, el disco. Pero
El Kratos ahí de discoplasticidad, he intentado Alejandro hacerlo mucho. Están haciendo ahora
lo del SPH.
Hicimos un TFM en metales y ahora está haciendo otro TFM, creo que es con hielo. Han visto que también tiene comportamiento viscoplástico. En la simulación, en el proyecto este del FatSAM, estamos mirando temperatura, pero también tenemos información, no la hemos incorporado, pero hay información de rate dependence, de viscoplasticidad igual, o sea que tenemos datos también en metal.
Pero este sí lo que es que viscoelástico. De hecho, retorna su configuración inicial, su deformación plástica, pero claramente es rate dependent. Estamos viendo diferentes velocidades y deformaciones máximas. Pero para una misma velocidad y deformación máxima, en un mismo sample que ya fue ensañado, la rigidez va. Entonces, viendo la clase, digamos, no tenía suficiente daño. Más o menos estamos claros que es daño. Pero por el momento que están en
Viscoelasticidad.
y hasta sin daño. No, porque si no, ya se me hace otro PhD aparte. Bueno, Javier, la verdad no es trabajo muy solamente. Javier está trabajando con un post de Miguel. Entonces, tiene una nueva formulación. Estamos trabajando para incorporar Bitcoin, termo y electro. Esa es la formulación.
Nosotros no usáis Kratos.
No. Mira, lo que hacen, hoy está en moda. Era alguien de aquí, que inició aquí. Es Badía, es un cambio. Entonces, Pero sí, así debería de ser algo que se da.
Sí. Sí, sí, sí. Nosotros tenemos ensayos de estos cíclicos, que son de empatía o plasticidad, y el daño aparece cuando estás en régimen de soporte. O sea, que no hace sentido que sea así en plástico, sino que no tiene el endurecimiento, todo lo que tiene eso, entonces arrancado el daño.
Exacto. Y digamos que ya se sabe, hay un efecto típico que le llaman el Mullins effect, ya se sabe que el primer ensayo de baja rigidez, etcétera. Pero esto es posterior a eso. Pues todos estos ensayos los hice posterior a haberlo ensayado a máxima velocidad, máxima deformación una vez. Y luego hacer todo lo demás. Entonces, sí, parece que tengo daño.
Parece que no hay daño. O sea, habría... ¿Cómo es la microestructura de esto? O sea, ¿es estructural por dentro?
No,
realmente es homogéneo.
Es homogéneo. Es homogéneo, pero es un polígono, ¿no? O sea, la idea de que son cadenas largas, no existe un concepto de microestructura. No. Lo que sí parece interesante es un material bien viscoso. O sea, cuando retorna se hace todo el buckling porque no se ha logrado regresar a tiempo. Y luego poco a poco se va bajando hasta que se devuelve algo. Pero bastante habría sido que la viscosidad la pudiéramos modelar, pero encima tener que poner
El daño. A ver, si quieres ponerle un modelo de daño básico como isótropo, no es tan complicado.
Sí, eso he estado viendo. Podría ser razonable. Lo único es que lo podría aplicar y haría sentido. O sea, seguro puedo reproducir esto a nivel de Gauss. Pero luego en la simulación, cuando haga una geometría, etcétera, y haga algo, no sé cómo se va a comportar. O sea,
hay que ver cómo se mezclan las cosas.
Exacto.
Las no linearidades, cada una por su cuenta.
Sí.
¿Quieres apuntar cosas?
Exacto. De nuevo, es otro PhD, así que...
Al siguiente.
Suerte al que le toque.
So what did you recommend install?
Visual Studio Code.
VS Code.
Yeah.
Yes.
I think it's V. No, it's not capital V.
No,
I mean, it's not V, it's V.
Yeah.
It's me.
Yeah, visual.
V from visual valor.
Yeah.
Visual Studio, people, yes.
Like
Visual
it's. I mean, I think that it's,
Microsoft, but
yeah, it's from Microsoft
free
because
to download.
the point is that Microsoft has a software to compile code, which is Visual Studio. And from that Visual Studio, then they develop,
An idea.
to be able just to read code, which is Visual Studio.
No, I worked with that before, but like the pronunciation, I don't get that. Because we just
Getting
like
safe,
visual
like,
studies, so I
Okay.
didn't get it, sorry. Okay, yeah.
Tenemos la opción de llevar todo lo que tenéis a Kratos y
También en otro PhD. Suerte. No, sí. Lo que decía, yo pensé cuando vine al inicio, porque yo ya conocía a Simple y sabía de Kratos, pensé que la respuesta iba a ser claro. Pero para este proyecto en específico,
depende de lo que vayan a hacer. Si hay mucha. Depende de lo específico. ¿Quién va a ser?
sí, eso. En el proyecto está esta gente de Cartagena que ya había avanzado en desarrollar código, etcétera, en esta plataforma. La idea era que nosotros solo nos íbamos a comentar en eso. Luego ya terminamos aprendiendo otro resto de cosas de esa herramienta, etcétera. Porque yo hago uso de modeling, no hago ni siquiera caracterización, realmente esto es un side project bien grande que me ha surgido. Yo hago full simulations, o sea, de todo el cuerpo con las condiciones, etcétera. Tratar de hacer algo con el uso de modeling.
Teorías.
Sergio, para encontrar un ejemplo bueno, lo verificó la parte del project parameters y el structural materials, ¿es solamente en Git lo puedo dar para correr o tengo que correr el Python
No, puedes hacerlo desde Git. Te abres el proyecto
Sí,
y en lugar de darle a Generate Files, le das a Run Without Writing.
claro, claro.
¿Te da algún error o algo?
Claro. Run no write.
Sí.
Sí, me tiro un error.
Venga.
Sí. Ahí no toqué nada. Cuando verifiqué los archivos le di a run or write. Muy insightful. Una última, capaz si era cuando estuve revisando el bloqueo eléctrico. No creo porque estaba full contra esto nomás, pero. No. O sea, no, Kratos desde equipo no. O sea, acá en Windows no, en la computadora de la oficina. La verdad que todavía no configuré ni el TeamViewer ni el NVIDIA. Lo voy a tener en cuenta.
Aquí quiero presentar los archivos de JSON, donde son los Vaya que no me guste dónde esté la
Sí.
secundaria o algo. Sí, lo único que no tiene bien resuelto desde el punto de vista es lo que yo de pantalla. El TeamViewer sí lo tenía. Ha mejorado, sí, lo del doble pantalla con...
Ya te sale, te puede salir un poco,
Sí, sí.
porque te salga una pastilla arriba para cambiarla.
Vale, pero yo lo que digo es, TeamViewer me permitía tener yo dos monitores en el sitio remoto y yo en mi casa dos monitores y tener una eso es horrible. Eso TeamViewer sí lo hace. Con el Chrome, con el Remote Desktop, esto no funciona. Y esto es la pandemia.
No, I don't know how like
Mira, eso era. Puede ser, porque pone el usuario, user y tal, que haya algún acento, que haya algún extra download que no le esté gustando y por eso hemos olvidado de esto, que suele ser que tenga posibilidades.
tengo este de ayer que pero y
Generate the mesh. Same that. Just try to help you collapse the model first. Then we select all the you are already, for some reason, even though you see you are inside Kratos. Yes. Once you are inside Kratos, you cannot mesh until you assign
No, para el almuerzo.
Basically, what I will be doing is we open Kratos because it's not in the
No eras aquí arriba. Yo me volveré a la terraza y a la segunda.
I will be sending
Hoy sí está Miguel. Ayer no había nada. No, por eso te decía.
Let's just leave it like
Para que conozca porque el público mira que le va a hacer falta. Se le va a acabar esa suerte. Y que se le acaba el contrato en agosto.
Kratos will
El proyecto se acaba en agosto.
have you know that you have
Vuelvo hasta el sol.
that can be meshed. It is only because the Kratos version was already open.
Y bien tener a alguien a quien preguntarle.
If you are just
Por lo menos
using
que
Java,
exacto, sí.
but once you open Kratos, you need first to assign the properties before meshing. So it was just a matter of
this mesh, do you need to make it smaller?
okay, you improve it. And if you want, you can then use triangles or quads, it's up to you, but it should be binary. Yes.
Prueba tomarles como decirle a Jenny sí, sí, para esta cosa. Yo les patrocino, pero pero
Toda tu tesis.
a veces
Por eso, tú asignas tablas cuando Alex no y ahora sí lo que haces tú. Aquí no puedes echar.
algunas veces ya ni eso, no estoy entendiendo, es un partner de discusión siempre y cuando sepa. Cuando se lo y pues arranco, o sea que cuando te corras para que te eliminen todas las. Ahora estoy llevando. De fatiga de las cosas se a ver, explica un poco.
Es directamente para
Sabieron porque tiene un nuevo equipo de nacionalismo de un capacitor y a ese capacitor le echas los capacitores pero hay que saber qué hacer con el capacitor abordarlo total que no le sabía nada y necesitaba participar de la discusión un día de Gemini ahí con este equipo aquí está y lo que hace es me explica un poco porque un conocimiento básico el tipo se termina ya te pone en una posición más intermedia. Claro, no te vas a hacer experto, pero puedes ya empezar a. Yo puedo entender como a los que estaban en ese momento y van a hacer un prototipo como armar fácil para poder participar y que hagan el prototipo. Algo tengo que saber. Claro. Vale, esto es pensando.
Pero I have a question. In order to create meshes and so on, it's a commercial one.
A ver, pero prefiero
I have things that I mean generate, because you're how to regenerate I don't know. Kratos will have techniques to do
No, todavía no específico. Te puede explicar los conceptos, pero en la página en Wikipedia.
I'm not sure how that's
Tengo hasta dos
in here. Because you
puños de
want to
texto, como los barajo para que me queden.
So, bueno, the first thing that you should be doing is select which is the material property or the variable to which from the
Casi lo mismo,
simulation
pero
that results in
a un nivel
which is more elements in this region.
si preparo,
Usually this is
que alguien te lo cuente. Sería el equipo que pensaría, pero no se
puede ser, más o menos.
No hay UI para
tengo el Google fuera del
I'm not sure. Neither I know about it. Quite powerful, but
No, but now
Porque sí que estabas estos días que
Y que sea para discutir un poco, te ayuda a pensar, hay que adquirir más sentido.
Maybe I have your
un poco la
sorry.
Vale, yo he preguntado esto, me ha dado esta respuesta. Esta no es buena por esto y por esto. Te va desbloqueando y te hace pensar, o sea, esto me dice, pero ¿y esto de aquí? Seguidamente dice,
Voy.
una cosa de la simplificación. Esto es muy claro. Esto es verificado.
Ahora vengo.
Un poco te ayuda a decir, intentaría probar esto. Más no, ojalá, más no es lo peor que lo mejor.
And then within the parameters of your exactly.
Entonces, a partir claramente para eso.
Yeah, that's what
Y ahí funciona
that's what I was having trouble. The simulation was
En
telling
mi
me.
caso, yo no he seleccionado el número de vehículo.
You're gonna get some parameter last
claro,
and you
pero
is what you
esto
said.
es para después de un
Sí, porque he ocultado la parte previa cíclica. La parte previa cíclica en realidad se queda en los intervalos. O sea, lo que vas a ver es que está yendo, subiendo, bajando, porque no avanza.
Because the right hand
No
side
avanza el tiempo,
says
se queda
0. So yeah, it should be 0 completo.
No, no, todo. Sí, sí, aquí está todo. Lo que no hay, creo que lo que yo os he dado, en realidad, no es -1, pero es -algo. Entonces tiene una parte que está en compresión. Entonces yo he limitado el valor mínimo a 0. Eso es lo único que he hecho. Eso es.
No, es cuando le diga a
Yeah, but I think it does that, but
claro.
the update doesn't need to be every cycle.
aprender qué es lo que yo tengo
It's
que
what it does in every 8 cycles. And
you
you just compute one cycle, and you only have this is what happened 20
ahora me
times.
imagino que
You compute another cycle, and this is all done.
Como son elementos, deberíamos estar en
Sí, para mí.
puedes poner
Yeah, exactly.
no aparece.
That's what I'm doing, but I'm having confusion. To launch it, what I've done it is instead of doing it through Kratos, because this is, you know, Python, to run a Python script, you need to have an interpreter. This interpreter needs to have the proper language. In this case, it needs to have just
O
Kratos.
sea, seguramente
Kratos is for all the
no sé si se ha parado la simulación o
If you run it through GID has developed its own interpreter with proper dependencies. If you don't, you have to get your interpreter and pip install.
son parte de los steps.
Exactly. But well, visual things, one thing is visual things, and the other thing is your interpreter. I don't know if you have Ben or Honda, whatever.
Aquí hay
Then you just install or pip install and well,
máximo,
correct.
mínimo, máximo.
You cannot do that. You can run it through
Lo comparas, ves que hay estabilidad.
Then you go to
Consulta el
Honda
interpreter
install. This would be very similar to this, but instead of pip, Honda install, Kratos physics Yeah.
me imagino que
For-
normalmente
What is given. What we've done, Kratos, the good thing about Kratos is that it has
ciclo
a
a ciclo, muy gradual,
open source and a Python interface,
no son
which is
visibles.
really easy because it's still in the background or
No, cualquiera, porque eso es Julián,
yeah, of course you can have it, but it's not open source and it's a bit harder to select.
¿Cómo es
Yeah,
tu
yeah,
carga
yeah.
física? Tu carga física, imagínate, tu material.
I've never worked, but
Tú vas a imponer una carga física. ¿Qué refiero con esto? Quiere decir, tú cargas, llegar a este valor de tensión máxima, por debajo de ti.
yeah.
No hay ningún tipo de no linealidad que era de estar.
You're running, you do your optimization in Python and then you ask for context. Yeah.
¿Dónde está?
This is the same.
Esta resistencia máxima empieza a bajar. ¿Cómo?
But this is the same.
Pues
It's
en
a
base
bit,
a
the thing is, yeah.
SU
It is a
actual,
lot.
voy a llamarle
It's
SU
easier
estrella,
than our
es igual a
But
SU inicial
no, the other way around.
Esta es la
It's
reducción de
less
propiedades.
optimized.
Lo mismo pasa con
And this,
la resistencia.
in the sense that Abacus doesn't have probably
¿Qué más está cambiando?
models for
cada vez
abrasion,
tiene
surface abrasion.
cómo está cambiando esta temperatura. De hecho, por hacer
Quiero hacerlo.
eso es así para que en cualquier momento tienes una respuesta de tipo
But can you add it?
en cualquier momento que esté habiendo una carga la respuesta reducida va a ser no lo sé, no ves. Por eso se llama invisible. Cuando yo aquí estoy aplicando ciclo, estamos hablando de material. Que yo vea,
Claro.
todo está controlado por eso. Y esto es una expresión matemática. Se está produciendo exactamente aquí. Este es el salto. Va a ir justo hacia que se produzca el cambio. ¿Cómo lo sé? ¿Hasta dónde estabas permitiendo todo el tema?
The thing is, here, since Kratos is people, somebody who now don't already use it. The thing is, you have to, that's the good thing about this. So they become a lot of PhD people that I just adding things. The thing is just, the problem with Kratos is just counts. It's not all the way, it's not optimized. Everybody that uses Kratos usually is adding
Pero hasta aquí todo es invisible.
So there's probably a lot of things already.
Hay degradación, pero no lo estás viendo. Que hasta que no hagas la carga no la vas a ver.
Entonces, en el caso límite que nosotros medimos a 5, 3, 7, 9, 8, nos vamos a 9, 9, 9, 9, 9.
¿Hasta cuál es el salto máximo que se va a dar? Pues el
Nonlinearity is material nonlinearity is there.
Entonces, para determinar esta FR máxima de salto, es de seguir partidos.
Exactly. But this works, but you're
La SI tiene que ser igual por FR, tiene que ser igual a S. Cuando esto se cumple, las no linealidades son ahí para atrás. Entonces, el número de ciclos que hace un ciclo,
everything is based on formulas. Amplias is like a version of that is really focused on we use FatSAM.
y a partir de aquí, la estrategia de avance, si no debe encontrar estabilidad, va a permitir dar nuevos saltos, pues ya son.
This is a software that is called What you do is you have Git, you have model, but you don't model.
Pues se llama Advancing Strategy, la cantidad de steps que tú le
what you do in this software is that you mesh, you define the mesh, you define the order of
de la carga
then you what you do is you prepare, so you assign restrictions, material, type of elements, etc. And then you compute with whatever model you have. So this you can also compute with
tipo de carga que vas a considerar como
big problem type.
Pero básicamente eso te permite hacer secuencias de carga.
Everything. You can use it for everything. And then you compute it with that model, and then you can see results.
Por el modelo solo de la partida de lo que vas a tener una respuesta de este estilo, y a partir de aquí hagas una carga física. Entonces, que ahora te permita volver a saltar para que la nonlinealidad Explicando qué quieres decir del modelo que se llama carga monotónica y que nombres de aquí son dos monos van a coincidir con los que los tres para la volcán y dos monos para la
Kratos is like and then
esto es lo que haría
there are like posts
para tú poder utilizar la ley de facilidad de los fundamentales tienes que con una ley de daño obtener el mismo tipo de respuesta monotónica
the problem is different.
que un método.
Almost all software that's different, which at the end of the day, in Kratos,
Y esto en general para los modelos de
it's
daño
just a software that gives you
gratis.
perfect parameters.
Si no me interesa,
The most important thing probably is the real.
para
This is the most important thing
puestos,
about
en lugar de
Kratos,
poner
which is
una ley de base
your global values, so position orthogonal, connectivity, net groups, which then you
no lo va a
refer
dar hasta ese nivel, lo va a dar hasta la Newton strength que coincide con el tiempo. Este tipo de curva es bien
It really depends. If it's a simple mesh,
hasta el
if
inicio
it's
de
a mesh with 5 elements and you want to test stuff, then yes. If it's a super complex mesh, yeah, you need a breadth.
Pero si se puede
I don't know if there's
El problema que quieras, pero la de pago de salida, de daño, de tranquilidad, lo que sea. Contratos puedo buscar en Maya, en geometría,
Yeah. I use
y luego puedo resolver con el modo que sea gratis.
Linux, but the thing is, it is not possible.
Sí.
And there's a problem with the values.
Desarrolla Kratos.
And when I change the Windows to my time text font, it says whatever it is. Sometimes it's an alien, No, I'm just, I started not long ago, but I think it's important.
Es que, si no te vas a descargar Kratos, te vas a descargar el código de
Yeah.
No, con Ricardo hemos estado más no sé bien lo que está, pero
No, sí, sí. O sea, tu estructura pones.
It's called solver. That does minimization.
Al todo amigo de.
So if you set up the
¿Cuál es la
airport,
actividad?
then you minimize it.
Environment. Y lo corres en el environment.
I would not.
Eso es lo que quiero.
People in industry really like the solver.
Yo he hecho la base de varios parámetros con el Kratos.
That's how they use it. Because Excel is everywhere.
Yes.
So if you could set up things in Excel and show them in Excel, people like it. Because it's, no one uses money. And even if you offer Python, it's most of the thing, well, all the actually Python can do anything. Even in Soul, an additional step they don't want to do.
They are paying for the license anyway, so they get the company for
It's because during learning, it makes sense to teach you as many tools as possible. But in industry, you gotta you have basic tools.
you end up in a company there's a small company that they don't have any.
So my experience is people love excellent tools.
But then you're right at the point that you find out an Excel from 1998 that has a build algorithm there to compute I don't know what. It becomes a mess.
I mean, if you ask me, do everything in your programming language, yes. Because of course, I cannot set up
an determinism or a particles are not important for them to say
En el servidor, ellos ponen los ficheros de
again,
input y corren
what everyone knows already uses.
Pero tienes que tener acceso a.
Sí, me parece que le da una capacidad o algo así para decorar.
I mean, it's not the optimal programming language if we can
I
say.
think like maybe it's like.
You don't even program.
Yeah,
You don't even, exactly, it's really, you can, now you can, as far as I understand, the latest versions of Excel, you can actually use Python. For macros instead of Visual Basic.
Maybe it's like just the basic things you should know.
Because
Knowing something exists is useful, then using it to its maximum extent, that's not necessarily as useful.
it's impossible to understand that. Impossible because when you catch, so what the use is not it's something like this is and one is there.
So it's like that.
Something like that. So
But your sample is this.
yes.
And this is like,
No, ni lo voy a usar, ¿no?
With and the machine the problem I have is I have to modulate some low, contain low, and also resist. But my problem is what? When I go on this, we have the global force. Because Abacus need to know what is happening. And since Abacus don't know what is happening, it's doing everything.
y poder experimentar fixed.
Pero está un poco capado. Para hacer eso tendrías sesiones Linux estarían sencillas
You are considering the
Creo que para YouTube está capado para todos los
claro, lo capa. Si tú pones una VPN, si YouTube, metes una VPN, entonces tendrías que instalarte Brave, entonces conectas, hay una versión de Tor, vas a Tor y desde Tor lo puedes ver. Eso es de cada la construcción para ver esas cosas. Porque si no, si YouTube ve que estás haciendo algo desde una VPN, tú estás canales con cosas, contenido que es capaz de encontrar aquí, pero los mandan. Es decir,
I mean, for me, you are indeed introducing this, right? It's like a simulation. So you have this. So basically you are using, you have
creo que ni lo podías.
corresponding
En la 1
model.
no el módulo, en la plataforma.
You are also introducing contacts for this region. Maybe the issue is with the contact.
Bueno, si tienes la
The contact in this region
pero yo creo que la
here,
1
with
puede que
last
tenga.
points which have contact, maybe are introducing some
No sé si tiene
weird noise that shouldn't be there. So what
Sí,
you
bueno,
can try to see if you are assuming that this is infinite region.
Sí, el problema es que esto
Here,
solo
this
no
infinite
tiene
region, and
tiene
there is
para directo,
a perfect
pero para
contact,
verlo
so
en
the
directo.
shape of this zone here is perfectly matching the shape of this layer, let's say, or apply the displacement. So instead of introducing this element, maybe you can just
Esto me pasa, por ejemplo, con los partidos de
This is
YouTube, ¿verdad? Que los de la liga más o menos
you can just
los
focus
en YouTube, los de Champions no están contados.
for this part here, you can instead of introducing a force or an element, maybe you can think in introducing an displacement on a line. So you know that all these points here will have the same, should have the same exact displacement compared to the infinite region. So in this way, maybe you will skip, or you will avoid having here some huge concentration.
Yo alguna vez que ha sido de los jóvenes de un curso así, por ejemplo,
And I tried just to see if it's a
pero
white
luego si vas a las contestas,
So what I
supongo que
did
te analizas,
is I took that, I created a cube, and I tried if I impose the same method, realize yes, the same as the force, and the force is the same. And for me, I don't have the same choice, the same concept. To see if it's a good one, it is not. And I tried on the cube, and no. And I know why. Because it's not the one because the cylinder are too big. The cylinders are like big cylinders.
Formas de pillarte la zona.
Since you're big, you have big.
Pero que decías una zona.
Es
un poco. Y digo lo de
Yo tengo página para los partidos.
Las calidades de
From my point of view, what you should try is while you are trying to start reproducing something, is trying to simplify it as much as possible. Because if you start introducing no linearities, then you kind of lose the control of what you are doing. And in here, even though this is elastic, finite sense but elastic, you have no linearity due to the contact. And maybe in order to start, you can try to start by substituting this contact by means of another thing. Yeah. So with the imposed displacement, it was even worse.
It was worse. And I tried this year, but the simulation was it was something. Okay, the case was good. I have a factor 2. This factor 2 for me, it just that for them, it's a 1 million that they did not. The cylinder pin on 2 we are 5 centimeters, 5 centimeters.
Which is the way in which they are measured.
Yo no
They are given forces
Y es más que la realidad en los niveles tampoco había dicho
The reaction.
los resultados son iguales ganar por un gol, empatar de 24.
Now we are okay.
Depende de si la misma
I
a mí lo que Rodrigo
asked them to
a mí lo que me ha parecido es pero a mí me ha parecido que bueno, más equipo que
Es un amarillo para nivel Champions.
pero dices tiene un balón de oro.
Sí.
No es malo, es un buen jugador. Un balón de oro. Pero porque no puedes ser
La fusión del balón de oro, los jugadores que aparecen cuando el partido está difícil y no aparecen. El de Francia, que para el fútbol, el de
Yeah, the input data cannot be measured under the most
Bueno, más lo que veo que fue en Portugal. Portugal sí es un equipo. Y ya lleva semifinal, me parece.
I don't know what to tell you.
Portugal igual, pero
lo que han puesto
Okay,
han sido lo que yo esperaba ver.
Sí.
Okay, we will close here this last hands-on session, and we will continue at 2:30